Hello viewers, welcome to the YouTube channel. In this video we will discuss class 12 or 2nd PUC Physics chapter 2, that is electrostatic potential and capacitance. One shot, from basic to advanced level, for board, JEE, KCET and NET. Subscribed, one comment for PDF. Do support, watch till end, don't forget to share, subscribe the channel. Let's start. Electrostatic potential and capacitance. Start with basic. Electrostatic potential or electric potential. Electric potential at a point in an electric field is the work done in bringing a unit positive charge from infinity to that point against the electric field. Or the work done per unit positive charge to move a charge from one point to another in an electric field. That is electric potential. V is equal to work done by charge. That is V is equal to W by Q. Here, SI unit is joule per coulomb or volt. Potential is a scalar. 1 volt is equal to 1 joule per coulomb. Next, potential difference. Electric potential difference between the 2 points is the work done by an external force to bring the unit positive charge from one point to another point. From figure, VA and VB. B potentials at 2 points A and B respectively in an electric field of strength E. Therefore, potential difference is equal to VB minus VA. Here, SI unit is joule per coulomb or volt. Potential goes on decreases along the direction of electric field. Note 1. Both electric potential and potential difference are scalar. 2. SI unit of both electric potential and potential difference is volt or joule per coulomb. 3. Electric potential at infinity is taken as 0. 4. Electric potential is the property of a point and is independent of the path traced by the charge. Electrostatic potential energy. Consider a source charge, Q. Let E is electric field due to a charge Q greater than 0, that is Q is the positive charge. Q0 is test charge. Q0 greater than 0, that is Q0 is the positive charge. When we bring a test charge Q0 from a point R to P, then Q charge produces repulsive force on Q0. Therefore, an external force is applied on charge Q0 to bring it from R to P. That is, external force is equal to minus electric force. Net force on test charge Q0 is equal to 0. As a result, the test charge moves with constant speed and with zero acceleration. The work done by the external force in moving a charge Q0 from R to P is WRP is equal to integration R to P F external into dr. Because let dr is equal to small displacement of Q0. dW is equal to small work done. Therefore, dW is equal to F external into dr. Therefore, total work done is equal to W is equal to integration of dW. That is equal to integration of F external into dr, where dr is equal to displacement. WRP can written as WRP is equal to minus integration R to P of F electric into dr. Negative sign indicates that work done is against electrostatic repulsive force. This work done is stored as a potential energy. At every point in the electrostatic field, the charge Q possesses certain potential energy. If R is at infinity, then W infinity P is equal to minus integration infinity to P of F electric into dr. But work done is equal to potential energy. Therefore, W is equal to U. Above equation written as U infinity P is equal to minus integration infinity to P of F electric into dr. Therefore, potential energy of a charge Q naught at a point is the work done by the external force to bring that charge from infinity to that point against the electric field. Next, derive an expression for potential due to a point charge. From figure, Q is point charge at origin O. R is distance between O and P. X is distance between O and A. Dx is distance between A and B. E is electric field due to point charge Q. Q naught is unit positive charge is equal to +1 coulomb. According to Coulomb's law, F is equal to 1 by 4 pi epsilon naught, Q naught by x square. But Q naught is equal to 1. Therefore, F is equal to 1 by 4 pi epsilon naught, Q by x square. Mark as equation 1. Small work done in bringing a unit positive charge Q naught from A to B is dW is equal to minus F into dx. Mark as equation 2. Negative sign indicates that work is done opposite to the direction of electric field. Substitute equation 1 into we get dW is equal to minus 1 by 4 pi epsilon naught, Q by x square into dx. Mark as equation 3. The total work done in moving 1c of charge from x is equal to infinity to x is equal to r can be calculated by using integration. Therefore, W is equal to integration infinity to r of dW. Substitute equation 3 in this equation we get W is equal to integration infinity to r of minus 1 by 4 pi epsilon naught, Q by x square into dx. Take constant term common. That is, W is equal to minus Q by 4 pi epsilon naught, integration, infinity to r of 1 by x square dx. On simplification, that is, integration of 1 by x square is equal to minus 1 by x. Substituting in above equation, we get W is equal to minus Q by 4 pi epsilon naught into bracket minus 1 by x infinity to r. The above equation can written as W is equal to minus Q by 4 pi epsilon naught into bracket 1 by r minus 1 by infinity, where 1 by infinity is equal to 0. Then W is equal to minus Q by 4 pi epsilon naught into bracket 1 by r. But V is equal to W by Q, where Q is equal to 1. That is V is equal to W. The final equation will be V is equal to 1 by 4 pi epsilon naught Q by r. This is the expression for electric potential. Next, derive an expression for potential due to an electric dipole. Proof. From the figure, consider an electric dipole AB having the charges plus Q and minus Q separated by a small distance to A. Let O be the center of the dipole and M be the point at a distance r from O. Let theta be the angle between dipole axis and the line joining the point and the center of the dipole. R1 is equal to distance between plus Q and M. R2 is equal to distance between minus Q and M. Therefore, potential due to plus Q at M is V1 is equal to 1 by 4 pi epsilon naught Q by R1. Mark as equation 1. Similarly, potential due to minus Q at M is V2 is equal to minus 1 by 4 pi epsilon naught Q by R2. Mark as equation 2. Potential due to dipole at M is the sum of potentials due to charges plus Q and minus Q. Therefore, V is equal to V1 plus V2. Substitute equation 1 and 2 in above equation. We get V is equal to 1 by 4 pi epsilon naught Q by R1 minus 1 by 4 pi epsilon naught Q by R2. On taking terms common, we get V is equal to Q by 4 pi epsilon naught into bracket 1 by R1 minus 1 by R2. Mark as equation 3. From triangle AOM and BOM. R1 square is equal to R square plus A square minus 2AR cos theta. And R2 square is equal to R square plus A square plus 2AR cos theta. Therefore, R1 square becomes, take R square common, we get R1 square is equal to R square into bracket 1 plus A square by R square minus 2A cos theta by R. If R much greater than A, then A square by R square can be neglected. Therefore, R1 square is equal to R square into bracket 1 minus 2A cos theta by R. Therefore, R1 is equal to R into bracket 1 minus 2A cos theta by R to the power 1 by 2. On taking reciprocal, 1 by R1 is equal to 1 by R into bracket 1 by 1 minus 2A cos theta by R to the power 1 by 2. Therefore, 1 by R1 is equal to 1 by R into bracket 1 minus 2A cos theta by R to the power minus 1 by 2. Using binomial theorem, we get 1 by R1 is equal to 1 by R plus A cos theta by R square. Mark as equation 4. Similarly, 1 by R2 is equal to 1 by R minus A cos theta by R square. Mark as equation 5. Substitute equation 4 and 5 in 3, we get V is equal to Q by 4 pi epsilon naught into bracket 1 by R plus A cos theta by R square minus into bracket 1 by R minus A cos theta by R square. That is equal to Q by 4 pi epsilon naught into bracket 1 by R plus A cos theta by R square minus 1 by R minus A cos theta by R square. On simplifying, we get V is equal to Q by 4 pi epsilon naught into 2A cos theta by R square. But 2A into Q is equal to P. Therefore final answer is V is equal to 1 by 4 pi epsilon naught into P cos theta by R square. This is the expression for potential due to dipole. Note 1. If theta is equal to 0 degree or 180 degree, then cos 0 degree is equal to plus 1 and cos 180 degree is equal to minus 1. V is equal to plus or minus 1 by 4 pi epsilon naught into P cos theta by R square. This is the expression for potential at a point on the dipole axis. Note 2. If theta is equal to 90 degree, then cos 90 degree is equal to 0. Therefore, V is equal to 0. Potential at any point on equatorial line is 0. Next, compare the variation of electric potential and electric field with distance. The graph shows the variation of potential V with R and field E with R for a point charge Q. They vary as V inversely proportional to R and E inversely proportional to R square. Here, if Q greater than 0, then V greater than 0. Both Q and V are positive. If Q lesser than 0, then V lesser than 0. Both Q and V are negative. If R is equal to infinity, then V is equal to 0. Potential is 0 at infinity. Next, to find potential due to a system of charges using superposition principle. Potential at a given point due to a group of charges is the algebraic sum of all the potentials due to all the charges. Let Q1, Q2, Q3 up to Qn be the point charges placed at distance r1, r2, r3 up to rn respectively from point P. The potential at P due to Q1 is V1 is equal to 1 by 4 pi epsilon naught into Q1 by R1. The potential at P due to Q2 is V2 is equal to 1 by 4 pi epsilon naught into Q2 by R2. The potential at P due to Qn is Vn is equal to 1 by 4 pi epsilon naught into Qn by Rn. According to superposition principle, net potential at P is V is equal to V1 plus V2 plus V3 plus so on plus Vn. Substitute values, we get V is equal to 1 by 4 pi epsilon naught into Q1 by R1 plus 1 by 4 pi epsilon naught into Q2 by R2 plus so on plus 1 by 4 pi epsilon naught into Qn by Rn. By taking terms common. Finally we get V is equal to 1 by 4 pi epsilon naught, summation of I is equal to 1 to n of Qi by Ri. Note 1. Potential due to a charged spherical shell at a point outside the shell is V is equal to 1 by 4 pi epsilon naught Q by R. Potential at the surface of spherical shell R is equal to R. V is equal to 1 by 4 pi epsilon naught Q by R. Potential inside the shells is equal to potential at the surface, whereas electric field inside the shell is 0. If you like the video, just like and subscribe, so I can come up with next topic quickly. Next. Equipotential surface. The surface with a constant value of potential at all points on the surface is called equipotential surface. Properties of equipotential surface. 1. Potential difference between 2 points on the equipotential surface is 0. Therefore no work is required to move a test charge on the equipotential surface. 2. Electric field is normal to the equipotential surface. 3. Two equipotential surfaces never intersect each other. 4. They are farther in the region of weak electric field. 5. Equipotential surfaces are closer in the region of strong electric field. Next. Shape of equipotential surfaces. 1. Equipotential surface for single charge is as shown. The equipotential surfaces are concentric spherical surfaces. 2. Equipotential surface for dipole. 3. Equipotential surface for two identical positive charges. 4. Equipotential surface for a uniform electric field. Next. Derive the relation between electric field and electric potential. Let A and B is equipotential surfaces. VA is equal to V is potential of A. VB is equal to V plus dV is potential of B. dl is perpendicular distance between A and B. E is electric field acting along A to B. E is equal to mod E is magnitude of electric field. Therefore, potential difference is equal to VA minus VB. Mark as equation 1. On substituting values of VA and VB, we get V minus V plus dV. On plus V and minus V get cancel, then potential difference is equal to minus dV. Mark as equation 2. Imagine unit positive charge, Q0 is equal to plus 1c, moves perpendicularly from B to A against field direction. Therefore, work done, W, is equal to potential difference. That is, W is equal to minus dV. But W is equal to F into dl. Mark as equation 3. Where E is equal to F by Q naught. Here, Q naught is equal to 1. Therefore, E is equal to F. Substitute this value in equation 3. We get W is equal to E into dl. Mark as equation 4. But W is equal to minus dV. On substituting in 4, we get minus dV is equal to E into dl. On equating, E is equal to minus dV by dl. This is the relation between field and potential. Note, for CET, NET. 1. The magnitude of electric field is equal to the negative potential gradient. 2. The direction of electric field is in the direction of decreasing potential. 3. Magnitude of field is the change in magnitude of potential per unit displacement normal to the equipotential surface at the point. Next, electric potential energy at a system of point charges. Potential energy at a system of point charges is the work done in bringing them from infinity to given positions. Next, expression for electric potential energy of a system of two charges. Imagine the charges Q1 and Q2 are at infinity. First, the charge Q1 is brought from infinity to the point A, and no work is done. This is because there is no electric field to oppose this charge. R is distance between A and B. Potential at P due to Q1 is V1 is equal to 1 by 4 pi epsilon naught into Q1 by R. Bring a point charge Q2 from infinity to point B, then potential is equal to work done by charge. That is, V1 is equal to W by Q2. On equating, W is equal to V1 into Q2. On substituting V1 value, we get W is equal to 1 by 4 pi epsilon naught into Q1 by R into Q2. But work done is stored as potential energy of system. W is equal to U. Therefore, U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R. This is the expression for potential energy of system of two charges. Next, expression for electric potential energy of system of three charges. From figure, consider 3-point charges Q1, Q2 and Q3 kept at a points A, B and C. Let R1, 2, R2, 3 and R1, 3 be the distance, position vectors. Therefore, work done in bringing charge Q2 from infinity to the point B is given by W1 is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R1, 2. Work done to bring Q3 from to C against repulsive force of Q2 is W2 is equal to 1 by 4 pi epsilon naught into Q2 Q3 by R2, 3. Work done to bring Q3 from to C against repulsive force Q1 is W3 is equal to 1 by 4 pi epsilon naught into Q3 Q1 by R3, 1. Total work done in assembling the three charges is given by W is equal to W1 plus W2 plus W3. Substitute the values, we get W is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R1, 2 plus 1 by 4 pi epsilon naught into Q2 Q3 by R2, 3 plus 1 by 4 pi epsilon naught into Q3 Q1 by R3, 1. Take 1 by 4 pi epsilon naught common, we get W is equal to 1 by 4 pi epsilon naught into bracket Q1 Q2 by R1, 2 plus Q to Q3 by R23 plus Q3 Q1 by R31. But work done is equal to potential energy. That is, W is equal to U. Therefore, U is equal to 1 by 4 pi epsilon naught into bracket Q1 Q2 by R12 plus Q to Q3 by R23 plus Q3 Q1 by R31. This is the expression for potential energy of system of three charges. Next, expression for electric potential energy of a single charge in an external field. From figure, imagine the charges Q1 Q2 are initially at infinity. First, the charge Q1 is brought from infinity to the point A, and no work is done for this, because there is no electric field to oppose this charge. Let E is an external electric field at a point P. V is an external electric potential at a point P. Q is any point charge. Therefore, the work done in bringing a charge Q from infinity to point P is work done is equal to potential into charge. That is, W is equal to U. Therefore, U is equal to VQ, where V is equal to 1 by 4 pi epsilon naught Q1 by R. Finally, we get U is equal to 1 by 4 pi epsilon naught Q1 Q2 by R. Next, expression for electric potential energy of a system of two charges in an external field. From figure, let E is external electric field. V1 is external potential at A. V2 is external potential at B. Work done to bring Q1 charge from infinity to A is W1 is equal to V1 into Q1. Work done to bring Q2 charge from infinity to B is W2 is equal to V2 into Q2. But to bring Q2 work is done not only against the external field D but also against the field due to Q1. W3 is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. Therefore, potential energy of a system is equal to W1 plus W2 plus W3. Substitute values, we get U is equal to V1 Q1 plus V2 Q2 plus 1 by 4 pi epsilon naught Q1 Q2 by R12. Next, derive an expression for potential energy of a dipole in an external field. Electric potential energy of an electric dipole is the work done in rotating the dipole from zero energy position to the desired position in the electric field. Torque acting on the electric dipole placed in an external electric field is given by Τ is equal to Pe sin theta. Mark as equation 1, where P is electric dipole moment, E is electric intensity, theta is angle between P and E. Small work done in rotating the dipole through an angle d theta without acceleration is given by dW is equal to τ d theta. Mark as equation number 2. Substitute equation 1 in 2, we get dW is equal to Pe sin theta d theta. Work done in rotating the dipole from theta 1 to theta 2. W is equal to integration theta 1 to theta 2 dW. Mark as equation 3. Now substitute equation 2 in 3, we get W is equal to integration theta 1 to theta 2 Pe sin theta d theta. Take Pe outside, then W is equal to PE integration theta 1 to theta 2 sine theta d theta. Here, integration of sine theta is equal to minus cos theta. Therefore, W is equal to PE into bracket minus cos theta from theta 1 to theta 2. Always take the above one first, that is theta 2. Therefore, W is equal to PE into bracket minus into bracket cos theta 2 minus cos theta 1. Therefore, W is equal to PE into bracket cos theta 1 minus cos theta 2. The work done is stored in the dipole as potential energy. That is, U is equal to PE into bracket cos theta 1 minus cos theta 2. But theta 1 is equal to 90 degree. And theta 2 is equal to theta. Substitute in above equation. U is equal to PE into bracket cos 90 degree minus cos theta, where cos 90 degree is equal to 0. Therefore, U is equal to PE into bracket 0 minus cos theta. Therefore, the final equation is U is equal to minus PE cos theta. Note 1. We have U is equal to minus PE cos theta. That is, U is equal to minus vector P into vector E. 2. We have U is equal to minus PE cos theta. Therefore, A. If theta is equal to 0 degree, cos 0 degree is equal to 1. Then, U is equal to minus PE. Potential energy is minimum and dipole is in stable equilibrium. B. If theta is equal to 180 degree, cos 180 degree is equal to minus 1. Then, U is equal to PE. Potential energy is maximum and dipole is in unstable equilibrium. C. Theta is equal to 90 degree, cos 90 degree is equal to 0. Then, U is equal to 0. Potential energy is minimum. Next, we discuss about some behavior of conductor in electrostatics field. Electrostatics of conductors. Conductors. The substance which allow electric charges to pass through them easily. Example: gold, silver, copper, human body, aluminium, graphite, etc. Conductors contain mobile charge carriers. In metallic conductors, example, copper, aluminium, free electrons are the mobile charge carriers. In metal, the valence electrons are the free electrons. They move randomly in different directions in the metal surface, but they cannot leave the metal. In the presence of an external electric field, the free electrons drift, move, against the direction of field. Note: in electrolytic conductors, example, NaCl, the charge carriers are both positive and negative ions. In this section, only metallic solid conductor is considered. Next, important results regarding electrostatic of conductor, metallic solid conductor. 1. Electrostatic field is 0 inside the conductor. When a conductor is placed in the external electric field, E external, the charge are induced on it due to induced charge on the conductor, electric field, E induced, is induced inside the conductor. E external and E induced are equal in magnitude but opposite in direction. The net electric field. E is equal to E external plus E induced is equal to 0. 2. At the surface of charged conductor, electric field must be normal to the surface at every point. 3. In a charged conductor, excess charges reside only on the surface in static situation. That is, no excess charge is present inside the conductor. 4. Electrostatic potential is constant throughout the volume of the conductor, that is, inside the conductor, and is equal to the value at its surface. 5. Electric field at the surface of a charged conductor is E is equal to sigma by epsilon naught into n cap. 6. Any cavity in the conductor remains shielded from outside electric influence. This effect is known as electrostatic shielding. Next is electrostatic shielding. Let's look definition and explanation. The electric field inside the cavity of a conductor is always zero. That is, the cavity of conductor remains shielded from outside electric field. This is called electrostatic shielding. Here, electric field inside the cavity of a conductor is always zero. To protect sensitive instruments from external field, they are enclosed in hollow conductors. Such hollow conductors are called Faraday cages. They need not be earthed. Whatever is the charge and field outside the cage, the instrument enclosed in the cage is protected from the external field. This is because of the charges resides or induced only on the outer surface of the cage. If the cage are earthed, the induced charges flow to the earth and the field beyond the region disappears. Next, applications of electrostatic shielding. 1. This effect can be made use of in protecting sensitive instruments from outside electrical influence. 2. Electrostatic shielding used to design TV cables, etc. 3. The metallic body of the car or bus acts as electrostatic shielding from lightning. Next, we look some basics. Polar molecules. The molecules in which the centers of positive and negative charges are separated are called polar molecule. Example, H2O, HCl. In polar molecule, the permanent dipole moment is present even in the absence of external electric field. Nonpolar molecules. The molecules in which centers of positive and negative charges coincide are called nonpolar molecules. Example, oxygen, nitrogen, carbon dioxide. In nonpolar molecule, the dipole moment is zero in the absence of external electric field. Next, dielectrics. These are the insulators which transmit electric effects without conducting the charges. Or, dielectrics are non-conducting substances and they do not have mobile charge carriers. Example, paper, mica, ceramics, pure water, oxygen, etc. There are two types of dielectrics. 1. Non-polar dielectrics and 2. Polar dielectrics. 1. Non-polar dielectrics. The dielectrics which made up of polar molecules are called polar dielectrics. Example, water. 2. Nonpolar dielectrics. The dielectric which contains nonpolar molecules are called nonpolar dielectrics. Example, oxygen. Behavior of nonpolar dielectric in the absence of external electric field. Nonpolar dielectric contains a nonpolar molecules. The centers of positive and negative charges are coincided, therefore dipoles are not present. As a result, Dipole moment is zero in the absence of external electric field. Behavior of nonpolar dielectric in the presence of external electric field. When an external electric field is applied to nonpolar dielectric, then dipoles are developed. As a result, net dipole moment is produced in the presence of external electric field. Behavior of polar dielectrics in the absence of external electric field. Polar dielectrics contain a polar molecule. The polar molecules have dipoles, but the dipoles are arranged randomly in the absence of an electric field. As a result, the net dipole moment is zero. Behavior of polar dielectric in the presence of external electric field. When an external field is applied to polar dielectrics, then dipoles are aligned in the direction of electric field. Therefore, the net dipole moment is produced. Next, polarization of dielectric. The dipole moment per unit volume is called polarization of dielectrics. That is, polarization is equal to dipole moment by volume. SI unit is coulomb per meter square. It is vector quantity. Next, dielectric strength. The maximum value of electric field strength of applied field up to which the dielectric breakdown does not take place. Dielectric breakdown means when a dielectric is placed in an electric field of very high strength, the electrons are detached from their parent atom and becomes free. Then the dielectric behaves like a conductor. This phenomenon is called as dielectric strength. SI unit is volts per meter or Newton per coulomb. Here ends with electrostatic potential part. Next starts with capacitors. Capacitor. Capacitor is a system of two conductors separated by an insulator to store electric charge and electric energy. Let's understand with diagram. A capacitor consists of two conductors having charges plus Q and minus Q, and potential V1 and V2 as shown in figure. The potential difference between the plates. V is equal to V1 minus V2. Here Q is called the charge on the capacitor. It is equal to the charge on one of the conductor. But the net charge of the capacitor is zero. That is plus Q minus Q is equal to zero. In general, Q is equal to charge of the capacitor. V is equal to potential difference between two conductors. Capacitance of a capacitor. It is found that potential difference is directly proportional to charge. That is, V directly proportional to Q, or Q directly proportional to V. This can be written as Q is equal to CV, where C is constant called capacitance of the capacitor, or C is equal to Q by V. Definition. Capacitance of a capacitor is defined as the ratio of charge on a capacitor to the potential difference between two conductors of the capacitor. S.I unit is coulomb per volt or farad, F. Next, definition of farad, denoted by capital F. Capacitance of a capacitor is said to be 1 farad, when 1 coulomb of charge given to it increases its potential by 1 volt. That is, C is equal to Q by V. If Q is equal to 1 coulomb, V is equal to 1 volt, then C is equal to 1 farad. Then, 1 farad is equal to 1 coulomb by 1 volt. That is, 1 farad is equal to 1 coulomb per volt. Farad is very big unit. In practice, the smaller units of farad is used. They are 1 millifarad, symbolically written as mF. Here, 1 millifarad is equal to 10 to the power minus 3 farad. 2 microfarad, symbolically written as μF. Here, 1 microfarad is equal to 10 to the power minus 6 farad. 3 nanofarad, symbolically written as NF. Here, 1 nanofarad is equal to 10 to the power minus 9 farad. 4 picofarad, symbolically written as PF. Here, 1 picofarad is equal to 10 to the power minus 12 farad. Next, factors on which the capacitance of conductor depends. Capacitance of conductor is the capacity to hold the charges given to it. It depends upon the following factors. They are: 1. Shape and size of the conductor. 2. The nature, permittivity, of the surrounding medium. 3. The presence of other conductor near it. Next, symbols of capacitors. A capacitor with fixed capacitance is represented with this symbol, and a capacitor with variable capacitance is represented with this symbol. Next, expression for capacitance of an isolated spherical conductor. That is, C is equal to Q by V. That is written as C is equal to Q by 1 by 4 pi epsilon naught into Q by R. On cancelling Q from numerator and denominator, we get C is equal to 4 pi epsilon naught R. This equation is for when conductor is placed in air. Similarly, C is equal to 4 pi epsilon naught epsilon R into R. This equation is for when conductor is placed in medium of dielectric constant, R, charges on two plates. Plus sigma and minus sigma reference, surface charge densities. And E, be the uniform electric field between plates. We have C is equal to Q by V. Mark as equation 1. And sigma is equal to Q by A. Mark as equation 2. Electric field due to plate 1 is E1 is equal to sigma by 2 epsilon naught. Mark as equation 3. Electric field due to plate 2 is E2 is equal to sigma by 2 epsilon naught. Mark as equation 4. In the region above the plate 1, E1 and E2 are in opposite direction. Therefore, net field above the plate 1 is E is equal to E1 minus E2. Substitute E1 and E2 values. That is equation 3 and 4. We get E is equal to 0. Similarly, E1 and E2 are in opposite direction in the region below the plate 2. Net field, E is equal to 0. Similarly, in the inner region between plates 1 and 2, E1 and E2 are in same direction. Therefore, net field E is equal to E1 plus E2. On substituting values, that is, E is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. On cancelling 2 from numerator and denominator, we get E is equal to sigma by epsilon naught. But E is equal to V by D. Substitute in above equation, we get V by D is equal to sigma by epsilon naught. Therefore, on equating, V is equal to sigma D by epsilon naught. Mark as equation 5. Substitute equation 5 in 1. That is, C is equal to Q by V. On substituting V value we get C is equal to Q by sigma D by epsilon naught. Taking epsilon naught to numerator, we get C is equal to Q epsilon naught by sigma D. Mark as equation 6. From equation 2, that is, sigma is equal to Q by A. On equating this equation, Q is equal to sigma A. Substitute this in equation 6. C is equal to sigma A epsilon naught by sigma D. On cancelling sigma, we get C is equal to A epsilon naught by D. This is the expression for capacitance of a parallel plate capacitor. Note: in case of a parallel plate capacitor, near the outer boundaries of the plates, the field lines bend outward at the edges. This effect is called fringing of the field. Next, derive the expression for capacitance of parallel capacitor when dielectric medium is present. Proof. Case 1. Consider a parallel plate capacitor. The space between the plate is vacuum. Let Q is charge on capacitor. V0 is potential difference. E0 is electric field between plates. Sigma is surface charge density. A is area of each plate. D is distance between two plates. Therefore, E0 is equal to sigma by epsilon naught. Case 2. When a dielectric medium is filled between two plates of a capacitor, then dipoles are induced. Let sigma D is surface charge density due to polarization of dielectric. ED is electric field due to polarization. But ED is equal to sigma D by epsilon naught. Therefore, net electric field, E is equal to E0 minus ED. On substituting values, E is equal to sigma by epsilon naught minus sigma D by epsilon naught. That is equal to sigma minus sigma D by epsilon naught. It is found that sigma minus sigma D directly proportional to sigma. Therefore, sigma minus sigma D is equal to sigma by K, where K is dielectric constant. Therefore, E is equal to sigma by epsilon naught K. Mark as equation 1. We know that E is equal to V by D. Equation 2. From 1 and 2, sigma by epsilon naught K is equal to V by D. On equating to sigma we get sigma is equal to V epsilon naught K by D. But sigma is equal to Q by A. On substituting, Q by A is equal to V epsilon naught K by D. On changing V and A, we get Q by V is equal to epsilon naught Ka by D. We know that Q by V is equal to C. Therefore, C is equal to epsilon naught Ka by D. Or C is equal to epsilon naught epsilon Ra by D. Next, expression for relative permittivity, dielectric constant, in terms of capacitance. Capacitance of parallel plate capacitor in absence of dielectric medium is Ca is equal to A epsilon naught by D. Mark as equation 1. Similarly, capacitance of parallel capacitor when dielectric medium is present is Cm is equal to A epsilon naught epsilon A by D. Mark as equation 2. From equation 1 and 2, Cm by Ca is equal to A epsilon naught epsilon R by D by A epsilon naught by D. On cancelling common terms, finally we get Cm by Ca is equal to epsilon R. Therefore, on equating to Cm, that is, Cm is equal to Ca into epsilon R. This is expression for relative permittivity in terms of capacitance. Now let's see factors on which the capacitance of parallel plate capacitor depends. Capacitance of parallel plate capacitor is 1. Directly proportional to the area of each plate. 2. Inversely proportional to the distance between the plates. 3. Directly proportional to the dielectric constant of the medium between the plates. How can you increase the capacitance of parallel plate capacitor? The capacitance of parallel plate capacitor can be increased by 1. Increasing the area of the plates. 2. Decreasing the distance between the plates. 3. Using a medium of high dielectric constant between the plates. Define dielectric constant. Dielectric constant is the ratio of capacitance of capacitor when space between the plates is filled with dielectric to the capacitance of same capacitor when space between the plates is vacuum. Next, equivalent capacitor and equivalent capacitance, effective capacitance. A single capacitor which produces same effect as that of set of capacitor is called equivalent capacitor, and its capacitance is called equivalent capacitance. Now we will see combination of capacitor. There are two combination. 1. Series combination. 2. Parallel combination. Let's study one by one. Series combination. A set of capacitors is said to be in series if they are connected end to end such that 1. The potential difference across the combination is equal to the sum of the potential differences across each capacitor. 2. The charge on each capacitor remains same. Let's derive an expression for effective capacitance of a series combination. From above figure, A and B are two capacitors connected in series. C1 and C2 are the capacitance of A and B respectively. V1 and V2 are the potential difference across A and B respectively. V is the potential difference applied across the combination. Let Q be the charge on each capacitor. Cas be effective capacitance of series. In series combination, total potential across the combination given by V is equal to V1 plus V2. Mark as equation 1. We have V1 is equal to Q by C1. V2 is equal to Q by C2. From 1, V is equal to Q by C1 plus Q by C2. On taking Q common, we get V is equal to Q into bracket 1 by C1 plus 1 by C2. Mark as equation 2. But, for effective capacitance of series, V is equal to Q by Cs. Substitute in equation 2, we get Q by Cs is equal to Q into bracket 1 by C1 plus 1 by C2. On cancelling Q both side we get 1 by Cs is equal to 1 by C1 plus 1 by C2. This is the expression for effective capacitance of two capacitors in series. For n capacitors in series is given by V is equal to V1 plus V2 plus V3 plus up to Vn. Therefore, 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4 up to 1 by Cn. This is the expression for effective capacitance of n capacitors in series. Next is parallel combination. A set of capacitors is said to be in parallel when they are connected between two common points such that 1. The potential difference across each capacitor is same as that applied across the combination. 2. The total charge stored in the combination is equal to the sum of the charges on each capacitor. Let's derive an expression for effective capacitance of a parallel combination. From figure, let A and B are two capacitors connected in parallel. C1 and C2 are the capacitance of A and B respectively. Q is total charge of combination. Q1 and Q2 are the charge on C1 and C2 respectively. V is the potential difference applied across the combination. Cp is effective capacitance of parallel. Potential difference across A is equal to potential difference across B. Therefore, in parallel combination, total potential across the combination given by Q is equal to Q1 plus Q2. Mark as equation 1. But we have Q1 is equal to C1V and Q2 is equal to C2V. From equation 1, substitute the values in equation 1, we get Q is equal to C1V plus C2V. Take V common. Then Q is equal to V into bracket C1 plus C2. Mark as equation 2. But if the combination is replaced by equivalent capacitor Cp is Q is equal to Cpv. On substituting above equation in 2, we get Cpv is equal to V into bracket C1 plus C2. Cancel V on both sides. Cp is equal to C1 plus C2. This is the expression for effective capacitance of two capacitors in parallel. For n capacitors, Cp is equal to C1 plus C2 plus C3 plus C4 plus up to Cn. Note 1. In series combination, charge on each capacitor remains constant. 2. In parallel combination, potential difference across each capacitor remains constant. 3. If C1 and C2 connected in series, then 1 by Cs is equal to 1 by C1 plus 1 by C2. Just cross multiply C1 C2 we get C2 plus C1 by C1 C2. Therefore, Cs is equal to C1 C2 by C1 plus C2. 4. For n capacitor in series, 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4 up to 1 by Cn. For n identical capacitors, C1 is equal to C2 is equal to C3 is equal to up to Cn is equal to C. Therefore, 1 by Cs is equal to n into 1 by C. That is, Cs is equal to C by n. 5. Capacitor are connected in parallel. Cp is equal to C1 plus C2 plus C3 plus up to Cn. Derive an expression for energy stored in a capacitor. Let plus Q and minus Q be charge on conductor 1 and 2 respectively. V1 and V2 be the potential of conductor 1 and 2 respectively. E be the electric field. Consider a capacitor which is initially uncharged. When a battery is connected across the capacitor, the charge transfer from one plate to another plate as shown in figure, as bit by bit in small amount dq from 0 to q. Consider an intermediate situation when the charges on the plates q and minus q. At this stage the potential difference between the plate is. Therefore, potential difference V' is equal to Q by C. Mark as equation 1. Here, dq is a small charge is transferred from conductor 2 to 1. dw is small work done to transfer dq. But dw is equal to V' into dq. Mark as equation 2. Therefore, dw is equal to Q by C into dq. Mark as equation 3. Total work done to transfer a charge from 0 to Q is W is equal to integration from 2Q into dw. Mark as equation 4. From equation 3 in 4 we get W is equal to integration from 0 to Q into Q by C into dq. Therefore, on taking 1 by C common, we get W is equal to 1 by C, integration from 2Q into Q dq. For integration of Q dq can be solved from this formula. That is, integration of x to the power n into dx is equal to x to the power n plus 1 by n plus 1. Here n is equal to 1. So, we can write as W is equal to 1 by C into Q to the power 1 plus 1 by 1 plus 1 from 0 to Q. That can be written as W is equal to 1 by C into Q to the power 2 by 2 from 0 to Q. On taking 1 outside, W is equal to 1 by 2C into Q square minus 0. Finally we get W is equal to Q square by 2C. Work done is stored as a potential energy. Here, work done is equal to potential energy. W is equal to U. Therefore, U is equal to Q square by 2C. This is the expression for energy stored. Here some other forms of expression is 1. U is equal to 1 by 2CV square. 2. U is equal to 1 by 2QV. Here ends the chapter 2.